Jai Hind everyone. I am Ankita Sharma working here in Ajay Kumar Garg Engineering College as an assistant professor. So today we are going to cover our complex topic number 5, that is program status word and addressing modes of 8051. So first of all, what is program status word? So program status word, that is known as PSW also. So it is just the flag register. It is the second name of the flag register. In microcontroller, the flag registers are also known as the program status word. It is of 8-bit. Just like in microprocessor 8085, the flag register is of 8-bit. So the program status word is also referred as the flag register. It is of 8-bit register. Out of these 8 bits, we use only 6 bits. So these 6 bits are used, and other remaining 2 bits, these are the unused bits which we use for the user. These are user definable, and out of these 6 bits, 4 bits we have that are conditional flags. So these 4 flags are conditional flags. So conditional flags means they vary from some conditions, like if there is some carry, for that it is carry flag, auxiliary carry flag, parity flag, and overflow flag. Just like in microprocessor 8085 and 8086, the carry flag was used to identify if there is a carry in the accumulator or not. In the result, is there any carry or not? So if there is any carry, then the flag bit will be 1. If there is no carry, the bit will be 0. Auxiliary carry, when the carry travels from the bit D3 to D4, at that time the carry which is transferring from, you can say that, from lower nibble to the upper nibble, that is auxiliary carry. Parity is if we have to check the number of ones in the answer, in the result, if the number of ones is an odd number, like 1, 3, 5, 7. In that case, the parity flag will be active or high, or we can say set, that is 1. And if the parity is even, it will be 0. So overflow flag is when the signed number given is overflowing, then it will be 1, otherwise it will be 0. So if you closely look at these 4 flags, carry flag, auxiliary carry flag, parity flag, and overflow flag, these 4 flags are having some condition. So that is why they are known as the conditional flags, because they indicate some conditions. Clear? And remaining 2 bits, that is program status word, 3rd bit and 4th. These are used for the selecting the register banks. As you all know that 8051 microcontroller is having register banks, different register banks. Out of these register banks, which register bank is going to used by the microcontroller? For that, these 2 bits are used, RS0 and RS1. So if you look here, this is the flag register D0, D1, D2, D3, D4, D5, D6 and D7. We can also write these flag bits as PS0, PS1, PS2, PS3, PSW4, 5, 6 and 7. So in exam, if a question comes where you have to find out what is the meaning of PSW.4, so that means PSW.4 indicates the D4 bit of the flag register. So 0, 1, 2, 3, 4, 5, 6 and 7. So at PSW 0, it is the parity. So as we have discussed, parity flag is set if the number of ones in the accumulator is an odd number. If the number of ones are even, then it will remain 0. So P is equal to 1, P is equal to 0. So P is equal to 1 means the number of ones are odd, and if P is equal to 0, so the number of ones are even. The number of ones will be even. Clear? So next is PSW1. It is a user definable bit. It is not used by the microcontroller. So this bit and this bit, D1 and D5. So D1 and D5, these are not used by the microcontroller. These are user defined bits. See, clear? Next is PSW, that is overflow. Overflow is used when the operation is too large and it needs some high order bit. So that is why the high order bit is overflowing from that, or that is why the sign bit is there. Next is these two bits, that is RS0 and RS1. So RS is register select bit 0, register select bit 1. So these two bits we use to select the register bank. If the value is 0, 0, then the register bank 0 is selected. If the value is 0, 1, register bank 1 is selected. If the value is 1, 0, then register bank 2 will be selected. And if the value is 1, 1, then the register bank 3 is selected. How it is done? Simple, 2 and 1. So these are the addresses which we used for the register bank. For register bank 0, the address 00H to 07H is used. For register bank 1, address 0820F is used. For register bank 2, address 10 is used. And for register bank 3, the address 1821F is used. Next is our fifth bit, PSW5. That is available for the user for general purpose. It is not used by the microcontroller. Next is PSW6, that is the D6th bit. It is an auxiliary carry bit. Auxiliary carry means when the carry is occurring in between the answer. Suppose we are having 8 bits in an answer. In a result, there are 8 bits. So out of these 8 bits, when the carry is transferring from D3 bit to the D4 bit, or we can say the lower 4 bits to the higher 4 bits. We can write it like this also. This is the D3 bit. We'll be discussing these flags in some examples in next few slides, so it will make it more clear. So D3 and D4. When the carry is transferring from D3 to D4, that carry, that intermediate carry is known as the auxiliary carry flag. So if there is some carry in between, it will be auxiliary carry flag will be 1. And if there is no carry, auxiliary carry flag will be 0. And simple carry flag when the result is having a carry. After 7th bit, there is an 8th bit. Or we can say after 8 bits, there is a 9th bit. After D7, there is D8. At that time, carry flag will be generated. So these are some examples from which we can find out the values. So the example is to show that the status of the carry flag, auxiliary carry and parity flag affect the addition of 38H and 2F in the following instructions. These are the two instructions. Hash 38H to A. So 38 is moved to accumulator. So 38 here is a data. Why? Because there is a hashtag in between. So accumulator is having value 38 and 2F is added to that. So 38 can be written as this in the binary number. It will be 0011 1000 and 2F is 0010 1111. If we add these numbers 00011 011 011 and here, if you look the values from here, it is 1 1. So 1 1 means 0 and carry 1. If we add 1 and 1, it will be 0 carry 1. And this carry is auxiliary carry. So 1 and 1 is 0 carry. There is a carry. So this carry is the auxiliary carry. So that means we will be having an auxiliary flag active. Next is, if we are adding these, so the answer is 67. So is there any carry? No, there is no carry here. We are only having 8 bits. So that is why carry flag is 0. Auxiliary carry flag is 1. Why? Because we are having a carry in between. That is from D3 to D4. And parity, if we count the number of ones, so 1, 2, 3, 4 and 5. So the number of ones here in the result is 5. So we are having 5 number of ones. So that is why it is an odd number and we will be having an parity. So parity flag will be 1. Next is, this is another example. If we add these numbers and we closely look, we will be having the answer this. So there is a carry here. There is a carry here. So 0, 0, 0, 0, 0, 0, 1, 1, 0, carry 1, 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 lastly 1, 1, 0 and carry 1. So there will be a carry in the last and there is auxiliary carry also here. So carry flag will be 1 because there is a 9th bit. Auxiliary carry flag is 1 because there is an intermediate carry, and parity is, if we find out, there is no 1 here. So parity will be even 0. There is no number of 1. No 1 is there. So that is why P is equal to 0 because it is an even number of ones. It has 0 ones. So next example, here is another example. Show the status of the carry flag, auxiliary carry and parity flag here. Once again, we are adding these two numbers and here you can see there is a carry in the last here. So that is why carry is 1. There is no intermediate carry between these two. So auxiliary carry will be 0. And the number of 1 here in the result, 1, 2, 3, 4. There are 4 number of 1s. So that is why parity is even. So P is equal to 0. So these were our flag registers of 8051. So if I do a comparison of all the flags of 8051, 8086 and 8051, 3 flags are common here. That is parity flag, carry flag, auxiliary carry flag. And in 8086 and 8051, overflow flag is also common. The work is common for both these, 8086 and 8051. So next topic is our 8051 addressing modes. Addressing modes is used to find out how the instruction is written, how the instruction can be presented, the address can be presented. So in 8051, we are having 6 types of addressing modes. First one is our immediate addressing mode, register addressing mode, direct register addressing mode, register indirect, indexed, and last one is our implied. So these 6 addressing modes will be used in the microcontroller 8051. So first of all, immediate addressing mode, as the name suggests, immediate, the data or the location is directly given in the instruction itself. You can transfer immediately. You have the address or the data. Next is register addressing mode. When the data transfer is done or the other operation is done in between 2 registers only. So that is why they are register addressing modes. Next is our direct addressing mode, when the address is directly given in the instruction or what we have to do is directly given in the instruction. Register indirect, when the address is indirectly given by the register. The register is pointing to the address. Indexed is when we have to use the program counter and data pointer or some other indexes for the addressing. And last one is the implied. In implied addressing mode, there is no operand given. The instruction itself have the opcode only the opcode is given and there is no operand, and we can easily find out what we have to do in that particular instruction without any operand. So this is the first example or the first addressing mode, that is immediate addressing mode. In the immediate addressing mode, the data is provided in the instruction itself and the data is provided immediately after the opcode. So as we all know, there is an opcode and after that opcode, the operand is given. So opcode is given and after the opcode, there is the data. So one thing before discussing, we should be aware about that in microcontroller, you will be seeing there is an hashtag symbol before some numbers. So this hashtag symbol indicates the data. or we can say there is a hashtag and 1 byte is given. So this will be used as a data, and if there is a byte given without a hashtag, so it will be treated as an address. So if a byte which is preceded with a hashtag is used as a data and a byte, simple byte is given, it will be used as an address. So if you look here, the example is move a comma hash 0AF. So 0AF H. H is for the hexadecimal number. Then why this 0 is here? This can be a question for sure. So 0 is added at the beginning. Why? Because when the data is starting from A to F, then the data should be preceded by 0 so that the microcontroller does not get confused with the alphabets or the hexadecimal numbers. So when we are using hexadecimal number 0 to 9, we can easily differentiate. So 0 to 9 can be easily differentiated. So A to F, if we are having a hexadecimal number that is between A to F, at that time these hexadecimal numbers will be used after putting a 0 between. So if I have to write out hexadecimal number A, E, A is 10 and E is our 15. So before that we will be using a 0. So it will be like 0AE hash. Next is our, here is another example. So if we look at this example, move a comma hash 0AF H. So what will happen here? This 0AF is used as a data. Why? Because there is a hashtag given, and this 0AF is transferred to accumulator. So after this instruction, after number 1 instruction, accumulator contents will be 0AF H, or we can say accumulator will be AFH. And we can write this in binary also. So it will be 10 10 11 11. So accumulator contents will be 1010 11 11. So next instruction is move R3, 45H. So here 45 is our data, and this data is immediately transferred to the register R3. We are having 8 registers here in microcontroller that are from R0 to R7. So 8 registers are there, and other than this, there is a register that is accumulator. There is an accumulator. There is a B register which is used for the multiplication and division instructions only. Next is our move DPTR. What is DPTR? DPTR is our data pointer that is of 16-bit. So that is why this 16-bit data is given here. So it is FE00 will be transferred to the data pointer. So the lower part will be given, will be copied to the data pointer lower. That will be DPTR. So DPTR lower part, lower 8 bits, and DPTR higher 8 bits. So here FE will be transferred here and 00 will be transferred here. And in these instructions, the hash symbol is used for immediate data, and 0 is preceded with the hexadecimal numbers. Next is our register addressing mode. In the register addressing mode, the source and the destination data should be present in a register, and the registers are from R0 to R7 or accumulator also. So if we look here, move a comma R5. So R5 will be the data of register R5 will be copied to accumulator. the register of accumulator will be copied to R0. This is another example of the immediate here. So in 8051, there is no instruction between move R5, R7. Like in microprocessor, we have to transfer the data between two registers. We were having 6 general purpose registers in microprocessor 8085. If I particularly talk about microprocessor 8085. So the instructions which we used to follow was these instructions we used to follow. Move A, B. The data is transferring between two registers. But here in microcontroller 8051, the data cannot be transferred between two registers. So move R5, R7 cannot be done. It is an invalid instruction. There is no instruction like move R5 to R7. So we cannot directly transfer the data between two registers from R0 to R7. Suppose I have to transfer the data between R5 and R7. Then what we'll have to do? We have to transfer the data from R5 to accumulator and then accumulator to R7. Indirectly, we can transfer the data between two registers, not directly. This is the register addressing mode. Next is direct addressing mode. The direct addressing mode is when the address is directly given. When the directly given address is directly given. In the direct addressing mode, the source of destination address is specified by using 8-bit data here in the instruction itself. So first, for example, move 80H, R6. So now 80H is a byte and this byte is not having any hash symbol. There is no hash symbol here. So the contents of register R6 will be copied to memory location 80. And here the contents at the memory location 45 will be copied to R2. The contents of location 05 will be copied to R0. So the first instruction will send the contents of R6 to here 80. The second will be having the address from 45 to R2 and next will be R0 to our 05. Next is our register indirect addressing mode. So in register indirect addressing mode, the source or the destination address is specified, is given in the register itself. So by using that register particularly, we can find out the internal or external addresses. So R0 and R1 we use for 8-bit addresses. Data pointer here in particularly these examples, data pointer is used for 16-bit addresses and no other registers will be used for addressing purpose. So accumulator can be used but not for the directly transfer. So move A, @R1. So before discussing these, we will be covering some instructions. So in the instruction, there is an @ symbol. So this @ symbol denotes that the particular register will be used as an indirect address. So here R1, @R1 means the contents of register R1. Suppose R1 is having value 51H. So this is the data on R1. So this 51H will be used as a memory location. So this 51 will be used as a memory location, and at this 51, when we look this 51 in the memory, so at this 51H there will be an 8-bit data, and that 8-bit data will be copied to our accumulator. So that is why it is called as the register indirect addressing mode. The address is indirectly given in the register. So R1 was having the data 51. That data was used as a memory location, and at that particular memory location there was 8-bit data, and that particular data was transferred to the accumulator. So this is the role of the indirect register addressing mode. Register indirect addressing mode you can say, or is indirect register addressing mode. So next is X. So here move X indicates that the external data memory is used. In microprocessor 8085, X indicated the extended pair. Suppose we were having HL pair, so we wrote only H at that time, not L with that. The X was used. For example, if I talk about 8085, it was LXI and then H. So this X was used as the extended pair. But here, this X is used to indicate that we are using the external data memory here, not the internal memory. And external data memory can only be accessed in the register indirect memory mode. Otherwise, it cannot be accessed directly. So now, if we look at this example, so in the external data memory, the value of that memory will be copied to the accumulator. The difference between these two instructions is, it is move A, R1, it is move X A, R1. The difference is only X. So this X indicates that the external data memory is used. Next is move X at the rate DPTR, that is data pointer, to accumulator. So the contents of accumulator will be indirectly transferred to the data pointer's address. This is also the register indirect addressing mode. Next is indexed addressing mode. So in the indexed addressing mode, if we closely look at that, in the indexed addressing mode, the source memory can only be accessed from program memory, and the destination is always the register A, that is accumulator. So the source will be our indexed source, that is source memory we can access from the program memory, and the destination is always the accumulator. So if we look here, this A is the destination because this is source and this is destination. The destination is fixed in the indexed addressing mode, so it is accumulator, and the sources can be program counter or the data pointer. And here C in the move C, you can see one C is written here and one C is here. So it is move C. The instruction is move C A, at the rate A plus PC. So accumulator plus program counter will be giving some address, and that address will be copied to the accumulator code byte. So A here is our code byte, and suppose we are having two addresses here. These are the contents. Suppose this is the content of accumulator 30 and 1125, it is the content of program counter. So if we add these things, A plus PC, the answer will be 1155, and at 1155 in the data memory, in the external data memory, at 1155 location, whatever the 8-bit data is given, that data will be copied to the accumulator. Similarly, the accumulator's contents will be added with the 16-bit data pointer's added address, and that address indicates to the some data, 8-bit data, and that 8-bit data will be copied to the accumulator. Last one is our implied addressing mode. In implied addressing mode, there is only the opcode given, and there will be single opcode will be given here. No operand will be given in the instruction itself. So here are the examples, that is RLA or swap A. RLA means rotate accumulator left, and swap means we have to swap the contents of accumulator. This is 1-byte instruction. Implied instruction, in implied addressing mode, all the instructions are of 1 byte only. Why? Because there is only opcode given. There is no operand given. No 8-bit operand, no 16-bit operand. Only an opcode that is of 1 byte. So the first one, that is RLA, it is used to rotate the accumulator register content to the left. Rotate accumulator left. For example, we can take an example for that. Suppose accumulator is having 1, 2, 3, 4. So these are the contents of accumulator. If we rotate them through left, all the bits will be shifted. It will be 0, 1, 0, 1, 0, 1, 0, 1. So the answer will be this after RLA. Next is swap. In swap, the lower nibbles will be transferred. So the lower 4 bits will be transferred to the upper transfer. Lower nibble. So suppose these 4 bits, these are same. So the 8 bits. So accumulators, upper 4 bits and lower 4 bits, these are swapped. This is implied addressing mode. Yeah, thank you.